Hello and welcome to this video. Today I would like to teach you how you can model exponential growths by finding a function that describes the exponential growth. And I would like to do this by using the number of people who are vaccinated against COVID-19 as an example to model exponential growth, because as you can see, this is quite a good example of exponential growth. So this curve shows the number of vaccinated people in Germany, but you can also do the calculations I will do now for your own home country. And one more thing I would like to tell you, please don't use this, what I'm going to do now, for real life calculations. And please don't try to seriously model vaccinations in the future by that what I'm going to do now. So this is the main message of this video should be teaching you how you can generally model a perfect exponential growth. Of course, reality is never perfect, and especially vaccinations won't go up exponentially forever. So this is really just teaching you how it works in general with the quite current example of vaccinations in this case Germany. So in order to model the number of vaccinated people exponentially, we first have to have a look at what or which parameters are important for exponential growth. And there are two main parameters which you should know if you want to model an exponential growth. So let's have a look at these two parameters. So this is how we would like to have an equation for the vaccinations dependent on the time t. So in this case, I would like to take February 1st as a starting point. So you always need to have a starting point for time t, so you have to define where t equals 0 is. And in this case, I would like to define t equals 0 at February 1st, because I've tried some different times for t equals 0, and if I take February 1st, it fits best. And of course, as I said, reality is not perfect, and this is why this won't give us a perfect model. And as I said, I've tried several models, and this one for t equals 0 here fits best. So let's just define t equals 0 as being February 1st, 2021. So this is what we have to think about first. What is t equals 0? And now let's just define t equals 0 should be February 1st in 2021. And thereby we have defined our starting time. So now, as you can see, we have three parameters here. T obviously is the time in days after t equals 0. So t should be the time in days after February 1st. And now we have to find out what a and k are. And these are two parameters who define our exponential function, our exponential growth. In order to find out what a is, we can just calculate v of 0, meaning the number of vaccinated people at t equals 0, so the meaning of the number of vaccinated people at February 1st. V of 0 is just a times k to the 0. Remember, we plug in 0 for t. K to the 0, or in general anything to the power of 0, gives us 1. So this is just a. So a is the number of people we have at t equals 0. So in general, a is always the number of, or the amount of things we have at t equals 0. So the amount you have at the beginning is a. And now we can just have a look at the statistics here. What is the amount of vaccinated people at February 1st? And it's, let me just have a look. It's 2.4% of the population. So I hope you see 2.4% of the population have been vaccinated at least once. So this is German for at least once. Okay, so let's just model our growth in percents. So let's not use the absolute numbers, but let's use percents. And if we use percents, so this in percent of the whole population of Germany, then a is equal to 2.4, because at February 1st, 2.4% of the German population were vaccinated at least once against COVID-19. So a is always the number of things, in this case vaccinated people, you have at the beginning. Now there's another parameter which is k. And k, this one, defines something which is called the doubling time. Now let's just talk about what is the doubling time. So let's just imagine the most simplest exponential growth you can imagine. 2 to the power of t, and t is the time in days, and just in this simplified model, let's just v of t be 2 to the t. Then we can see at t equals 0, we have exactly 1 vaccinated person. Then at t equals 1, we have exactly 2. At t equals 2, we've got already 4 vaccinated people. At t equals 3, we've got already 8 vaccinated people, because 2 to the 3 is 8. So in this case, every day the number of vaccinated people doubles. And this is why this is called the doubling time. So doubling time is the time within which a certain amount doubles. And now what we have to find out is the period of time where or in which the number or the percentage of vaccinated people in Germany doubles. And from this doubling time, we can then find out what k is. So k is not the doubling time itself, but we can find out k using the doubling time. And the question is, how can we do this? Sorry, that was my phone. Okay, so before we have a look at the statistics and have a look what the real doubling time is, let's just talk in general about how we can find out the doubling time. So if we have a look at the amount of vaccinated people at the point in time t, so t days after February 1st. Let's have a look at this amount, and then let's have a look at the amount after the doubling time. So capital TD, let's just call this the doubling time. So we have a look at the number of vaccinated people at time t, and then put the doubling time on top of t. And per definition of the doubling time, the number of vaccinated people at this point in time is double the number at this point in time, because we just moved the doubling time forwards, and within this time the number doubles. So twice this amount of people equals this amount of people, and this is the general formula how to find out k. So just this thought, if we have a point in time and then we go on td days, so the number of so the doubling time number of days, we have double the number of vaccinated people in this case. And now we can just plug in our general formula for v of t. So 2 times, in this case, a times k to the t equals 2 times a times k. What we plug in for t now is t plus td. So t plus td. And of course we could also have plugged in a equals 2.5, but the funny thing is we can divide by a, so a cancels out. And also we can divide by 2, so 2 cancels out as well. And we are now left with k to the t equals k to the t plus td. And by certain laws of mathematics, we can just rewrite this term here as k to the t times k to the power of td. This is the same as k to the t plus td, simple laws of exponentiation. And then let's divide again by kt. And I've realized I've made a mistake above. This 2 is too much, okay? I'm sorry. So this is 2, this is twice v of t, so this 2 is correct, but this is just once v of t, so we cannot cancel out the 2. This 2 is wrong, and this 2 cannot be cancelled out, so it has to be here as well. Here as well, sorry, now it's right. Okay, let's just divide by kt, then this cancels out with this, and we've got 2 equals k to the td. And now in order to get k, let's just erase the whole thing to the power of 1 divided by td. Then this just fades away, so we are left with k, and on this side we have 2 to the power of 1 over td. And this is how we can find out k, the parameter k. We just have to know td, so the doubling time, and then k is 2 to the power of 1 over td. Or you can also write this as the tdth root of 2, as if you prefer to do so. Now let's just find out what the doubling number is in this statistics. So at February 1st, as we know now, we've got 2.4%. Now we are looking for the point in time where we've got 4.8%, so double the number. Let's just have a look for 4.8%. This is the case on February 26th. So from February 1st to February 26th, it's 25 days. So the doubling time in our case is just 25 days, meaning that k is 2 to the power of 1 over 25. And now we've got every parameter we need in order to create our exponential function to model the number of vaccinated people in Germany. So we know a is 2.4, we know k is 2 to the power of 1 over 25. So v of t is equal to a times k to the t. So a times k to the t, which can be simplified to, so 2.4 times 2 to the t over 25. And this is our function, our model function, which gives us the number of, or which gives us the percentage of people in Germany who are vaccinated against COVID-19 at least once. And now we can just try this formula by plugging in some values and checking if they are correct. Okay, let's for example have a look at the value at 1st of May. 1st of May is 89 days after February 1st, if I've calculated that correctly, and even if not, it's close to 89, but I hope it's right. So let's just have a look at the real value, which is given by the statistics here. So let's have a look at May 1st. May 1st is just there, and we've got 28.2% of the population were vaccinated at that point in time. So May 1st. There you go. Sorry. I think there you go. 28.2% is the percentage of vaccinated people at May 1st or on May 1st. So now let's just plug in t equals 89 in our formula. So 2.4 times 2 to the power of, oh sorry, that was the wrong button, 2 to the power of, t is 89 divided by 25. We expect a result of 28.2, and our model gives us 28.3. So it's quite, or it's almost 28.3%. So it's quite an exact model, I guess. Let's maybe check some other values as well. So as you can see, the real number or the real percentage on April 1st is 12.3%. April 1st refers or is linked with t equals 59. So it's, I forgot it, it's 12.3%. And let's just plug in the value of 59 into our formula. And I've done that already, and it gives us exactly 12.3. Or not exactly, but almost exactly 12.3%. If we round the number. So I'm quite proud right now actually, because our model holds quite good in this period of time between February 1st and maybe May 1st. But as you can see in this diagram, this growth isn't really exponential anymore when it comes to the end of May. So here it's growing exponentially, going up, and we would expect something like this. But it does this. So we can see that these models don't always describe reality perfectly, especially in this case, because you can't vaccinate more people than there live in people in Germany, and we've got a little bit more than 80 million people. So latest at that point, this growth would stop, and then we've got not enough vaccines, and there are people who don't want to be vaccinated, and all these factors play into this growth. But at least at the beginning, we can really model this growth by an exponential function. We can just, to show you that this function doesn't really hold anymore for the end of May, so for the current time, I can prove this to you by plugging in the most current value we've got here. So the most current value the statistics give us is May 24th. Which is t equal to 112, and this value is here 40.7%. So we expect something like 40.7%. And if we plug in 112, this actually gives us something much more, so it's 53.6%. So 53.6%. So as we can see, these exponential growths are helping us to model reality within the first few days, or in this case months. But in the real world, growth starts to decline again after a few periods, or after a certain period of time, because we have only finite people on the world, so this couldn't go up exponentially forever. And as I said, many factors play into this growth as well. But I hope I managed to explain to you how you can, in general, model an exponential growth, especially if you are in your ideal mathematical world where no limit is set when it comes to upper bounds. And in this case, you can really model it by this. A is the number of people you have at the beginning at t equals 0, and you can calculate k by measuring the doubling time of this, or of the amount the function is about. Okay. I hope that was an interesting video for you to watch, and if you've got any questions, you can always ask them to me in the comments. If you've got any recommendations what I could do a video on as well, you can also just comment them under this video, and I'm looking forward to reading your comments. Thank you for watching my video. If you liked, you can hit the like button, you can hit the subscribe button, you can hit the bell to be notified with my latest, or by my latest videos. And yeah, stay healthy, and if you have been, thanks for watching.